All right, let's talk about carboxylic acids and their reactions. Of course, the one we've studied in Gen Chem many times is that carboxylic acids, like acetic acid, for example, will react with bases such as sodium hydroxide, affording the carboxylate salt of our acid, along with some water. And while that's very exciting, we can take this and react it further, forming esters by reacting carboxylates with an alkyl halide of our choice. So if we take acetic acid, for example, react it first with sodium hydroxide, and then how about ethyl bromide? We will end up with the ethyl ester here. And I'll go ahead and highlight the ethyl group that's being added in purple here so we can see where that's coming from. So we're going to take our carboxylic acid, react it with the salt, and then form that carboxylate, which then can be nucleophilic and will attack an alkyl halide, giving us the ester. So we can make the ester just by, remember, Fischer esterification we've looked at before previously, right? If we took that ethanol, acid, and heat, we would end up getting the same product. So using ethanol instead. So multiple ways to get there, right? And of course, we could first activate our carboxylic acid. We could turn it into an acid chloride first, and then go ahead and use one of these esterification mechanisms to get our product. So lots of ways to do it. That's the beauty of all this. There is one reaction that I had forgotten to cover last video, I think was on esters, so here we go. We do have a reagent which normally we use on nitriles, so I normally cover it in the nitriles, but it also works on esters, and since I covered esters first, we should go over that. There's a reagent called dibol. You may see it certain ways. You may see it as dibol with an H instead. You may see dibol -H. They all mean the same thing. It's a diisobutyl aluminum hydride. So we've got the aluminum hydrogen bond and then all of those lovely isobutyl groups on it. That's dibol there. Or you might see it as diba or dibol H, dibol hydride. Any of those are common. I use dibol. That's just the way I learned it, but I think the book uses diba. So you might see it in multiple ways. So just be aware of that. What this does is it turns an ester or a nitrile into an aldehyde. So it's our way of, instead of having the, you remember with carboxylic acids and the anhydrides, we had a special lithium, aluminum, all those alkoxys, and then the hydride. For esters and nitriles, we use the dibol. So we have slight tweaks to all of these to get them to work properly. Because these esters and the nitriles are a little less reactive than our acid chlorides and anhydrides are, so we have to use a different reagent for them. This reduces nitriles also to aldehydes. So we'll have that. So just be aware of that. It'll take your ester or nitrile and convert it into an aldehyde. Our last reaction of the acids that we're going to cover is when using lithium reagents. So not lithium cuprates, not the Gilmans, but they're going to react similarly. If we take a carboxylic acid, we'll use our favorite acetic acid this time, and we put 2 equivalents of some organolithium reagent in there, followed by an acid workup, you end up getting your ketone. So this will be how we're going to not use the Grignard, because remember, Grignard will go ahead and throw away, we'll just destroy our thing completely, go all the way down to the alcohol. For the Grignard, you will need 3 equivalents, right? First equivalent to deprotonate, second equivalent to add the first time, third equivalent to add the second time. So you need quite a few of the Grignard. And indeed, the organolithium here will function similarly. Our first step in this reaction is to deprotonate the alkoxy, or rather the carboxylic acid. So we have our alkyl lithium here. First step of this mechanism is a deprotonation. And in doing this, we will end up with our carboxylate, which now will be attacked by our second equivalent of our lithium reagent, which will pop open our carboxylate. And now we end up with an intermediate that is tetrahedral, as before. We have the 2 diolithiates here, along with our new methyl group. And I'm going to put our new methyl group, actually, let me put it in purple, just so we can see what's happened there. So we've added our CH3 on whatever our lithium reagent happened to be. And now we have both alkoxides with the lithium on it. And this is actually stable. You can isolate this with the 2 lithiums there. And upon acid workup, of course, we know that we have when we have geminal diols or hydrates, when we put those with water, we can get that equilibrium between the hydrate and the ketone. Right? This was one of our aldehyde ketone reactions. So with the H3O+, it gets rid of those lithiums. You have the 2 alcohols then. The alcohols will come down, kick one alcohol out, and you'll be left with your ketone as a result. And I'm going to put our purple methyl group on there. So it's a way of making ketones out of the carboxylic acids, and we use 2 equivalents of a lithium reagent. First equivalent becomes just an alkane, right? We're gonna lose methane through this first step. That's gonna bubble away. Second one gets added actually to the carbonyl, forming the 2 alkoxides with their lithiums to stabilize, and then an acid workup later will condense that carbonyl back down again. And so, in summary, with carboxylic acids, we can react them with a base, forming the carboxylate. Carboxylates are nucleophilic, and so we can treat them with an alkyl halide to produce an ester. We've also seen previously we can make esters through the Fischer esterification, which is treating an acid with an alcohol in the presence of acid and heat. And that's reversible, right? We can hydrolyze esters in either acidic or basic conditions to get back to the carboxylic acid. Esters can also be reduced by Diebol, gives us an aldehyde. And then finally, we can turn acids into ketones by using organolithium reagents. So just your alkane, or alkyl group rather, and your lithium, you'll have that negatively charged alkane bit and the positive lithium there. It's a salt. And so you have a very strong base there, so it's going to go ahead and deprotonate, and then it will go ahead and attack, adding itself on, giving you the ketone. In our next video, we'll take a look at amides, and then nitriles